The summing amplifier. Summing amplifier is used to combine multiple input signals from different devices. Primarily it's used in audio mixing equipment to send multiple inputs, like for example a microphone and a guitar and a keyboard, to combine those signals and then send it to one set of speakers. Now the circuit diagram summing amplifier, the circuit diagram, positive supply, negative supply, output voltage. Here's a 0 volt connected to my non-inverting input to serve as a reference. My inverting input feeds to V1 and R1. These connect to a feedback resistor like that. Now this would be my first channel, for example the microphone. My second channel, for example, could be a keyboard. That'll be V2 and R2. And then it keeps going as many devices as I want, and I'm just going to, for simplicity's sake, say this is Rn and that is Vn. Okay, so if I've got 10 inputs, this will go all the way up, duplicated up to V10 and R10. Now the way that it operates is, if we ignore that for a second, we can see it works exactly, it looks exactly the same as an inverting amplifier. The only difference is now that V1 will be amplified to the ratio between R1 and RF. V2 will be amplified to the ratio set by R2 and RF. And Vn will be amplified to the ratio set by Rn and RF. If all three of these, if all my input resistors have the exact same value, then we call this a loaded summing amplifier. Okay, again, each channel is amplified according to the relationship between its input resistor and the feedback resistor. As a result, my formulas, or the formula, will look as follows. If this is not loaded, in other words R1, R2, Rn have different values, then V out is equal to minus V1 times Rf over R1 plus negative V2 Rf over R2 plus, and so on until I eventually get to Vn times Rf over Rn. Okay, if it's loaded, you can go do the maths yourself and simplify this. Then V out for a loaded is equal to Rf over Rn, because they all the same value. That's a negative, and I'll multiply that with V1 plus V2 plus Vn. Okay, waveforms, V1, V2, V3. Let's say this is loaded. If I connect a sine wave there, and a sine wave there, and a sine wave there, then my V out is going to be equal to this sine plus that sine plus that sine all together. Now we can see from the diagram that this is one block, one block, one block high, so this will be in total 3 blocks, as those signals are all the same. the differentiator. Differentiator operates on the principle that the output voltage is equal to the rate of change of the input voltage. Okay, we're going to look at the discrete circuit. Discrete circuit, we've got Vin connected to a capacitor, and those connects to my resistor on the output. Now remember, the resistor is my output, so if I have current flow through the resistor, that means I will have a voltage on my output. As soon as the capacitor is fully charged, my resistor will not conduct, and because it doesn't conduct, its voltage will be 0. So the rate of change will work towards my output voltage. This is the discrete circuit, easy to remember. Capacitor, 2 F's represent the 2 sides of my plate of the capacitor. For the op-amp circuit, before we get to the op-amp circuit, let's look at the operation of this one. Okay, when I supply an input that is a square wave, let's do it over here. Okay, we can see Vin is a square wave and Vout. Remember, when a capacitor charges, it initially has maximum current flow, which means we will have maximum voltage on my resistor the moment that the current flows. Then, as the capacitor charges, that voltage will decrease over time, and that causes a spike to occur like that. When my voltage drops, so does the current, because now the current is flowing in the opposite direction, so my output voltage will go to a maximum negative and then charge or decrease as the capacitor's voltage increases, and then the same for that next one. So we can see it converts a square wave into a triangular wave. Now, if I change this ratio, because remember, the time ratio, or the time constant, is equal to R times C. So if I change this frequency, or these values, then the rate of charge is going to differ. So as a result, I can, in essence, convert my square wave into something that could look similar to a triangular wave if my frequency of the input is more accurate. If I supply a sine wave on the input, because of RLC circuits, all that's going to happen, if that's my input, my output is going to shift by 90 degrees because of the charging and discharging of the capacitor. And that's my passive circuit. The longer the time constant is, the shorter this pulse or these spikes are going to be. For the op-amp circuit, we've got Vin that goes into my capacitor, that feeds into my inverting input. My non-inverting input becomes a reference voltage. I've got minus V and I've got plus V to serve as the supply. Then I've got my feedback resistor that feeds from the output voltage. Okay, now again, the output voltage is equal to the rate of change of the input. And we still have this scenario where we've got the capacitor and the resistor. Now, do not think of this capacitor as a capacitor, rather think of it as an automatic variable resistor. Remember, the moment we connect a voltage onto a capacitor, the voltage on that capacitor is equal to 0. But as that capacitor charges, it now allows for an increase in voltage, which in terms refers that its resistance is increasing. So if we look back and consider our feedback calculations, V out is equal to minus RF over Rn. So if that starts at 0, I will have almost infinite gain, and then as that capacitor charges, its voltage increases, which means its resistance increases, and as that becomes larger, my output voltage will in turn get smaller over time. Okay. In order to calculate the output voltage of my op-amp differentiator, V out is equal to minus R times C, where that is R and that is C, and I multiply that with the change in my input voltage divided by change in time. And that is the differentiator. Last thing to remember, ideal application of the differentiator circuit is it applies or is applied as a high pass filter, which means high frequencies on the input it'll allow to pass, but the moment I allow a low frequency, the capacitor gets fully charged and my output becomes 0, so it blocks my low voltages or low frequencies from the input.